okay? Then what if there's multiple users are coming together, meaning you have to share the medium? What you gonna do? Then MAC. And it is very common. The sharing medium is very common in the wireless network. Then we talked about how we're gonna do is wireless multiple access. So today, in one most successful example of the wireless network, which is Wi-Fi 802.11, then we're gonna talk about Wi-Fi today. So wireless local area network. So we may say MAN, metro area network, WAN, wide area network, and sometimes we call the PAN, personal area network. Okay, so all these things are moved to SD, SD-MAN, SD-WAN, SD-WAN, SD-PAN, software defined WAN. Even we are doing the wireless or the network, we always do reconfigurable. Then we call the software defined WAN, software defined LAN. So we're gonna talk about more. So your final project is related to this. So what is 802.11 means? So I understand wireless network. Then what is 802.11 mean? So in the International Institute IEEE, International, what is IEEE in the full recommend? IEEE. Institute of Electronical and Electronics Engineering. So they are very powerful, and who made the standard? Okay, so 802.11, let's go to share. So 802.11 has many standards, starting with so 802.11 decides how you communicate. Something like 802 means network, 802. So 802.1 is the LAN protocol, and LLC Ethernet is 802.3, token bus 802.4, so 802.6 is MAN, and fiber optics is 802.8. And among those, we are talking about 802.11, which is most successful. So that is a Wi-Fi, wireless LAN, and mesh network. So 802.11 A, B, C, D, E, right? We now call Wi-Fi 1 and Wi-Fi 2. We will discuss about today. So 802 is in the view of the network. IEEE decide many standards. And if you want to join the communication link, meaning if your device need to be mixed with the existing network, you have to follow this standard. If not, it is if you are not following it, then it is contraband, and your device won't be used by the US and all Europe and all Asia. So Huawei, it's a political issue, but Huawei had some issue. Then they banned using on IEEE devices, meaning Huawei device is not able to use Wi-Fi, not able to use LTE. That's really powerful. It never happened, but they did some in a political way. In technical way, it doesn't make sense at all. Okay, go to the SharePoint. Now we understand, oh, wireless LAN, wireless PAN and MAN and WAN, and 802.11. Oh, 802 is related to network, and 11, among those, 11 is wireless. Okay, IEEE 802.11, IEEE, IEEE, so we usually pronounce it IEEE. IEEE has defined the specification for wireless network and called IEEE 802.11, which covers physical and the data link layers. Okay, we have to understand physical and data link layers. We know what that means, right? Then let's look at the BSS. BSS is basic service level, basic service set. So BSS and BSS with AP. So this is more common. So we have AP and you guys are connected around it. That we call infrastructure mode. Infrastructure mode, there is a leader And we are following the leader and dominated by the leader. Leader has internet connection, and we get internet connection via this leader. How about this? Walkie-talkie kind of things. I want to talk to the others, and the other want to talk to the others. If one of them has the internet connection, then we can connect to the internet. So among those, station to station, your notebook comes with the ad hoc mode, and every device in your Wi-Fi device, your phone comes with ad hoc, but it is not commonly used. So ad hoc meaning you can talk to each other without AP. So this is more common in our case, right? But when IEEE set the standard, your device must support two modes. One is ad hoc mode, the other is infrastructure mode. So we call this basic service set. Basic service set. This is basic service set without the AP. This is basic service set with the AP. Okay, we now understand what is a basic service set. The very basic set. So there is ESS, extended service set. So BSS and ESS. ESS is setup BSSs. Then BSS are connected to the backbone, and they are connected by our server. What does it look like? This is more like IGC guest Wi-Fi. They are not just one AP, they are multiple APs. Wherever you go inside the building, you are connected to IGC guest, right? They are controlled by the distributed system, and SUNY Korea server maintains your connection and monitor your connection. Okay, so now we understand what is BSS and ESS. Then let's look at the standard. Yep.
Question about the ad hoc. Can our laptops also broadcast signals to others?
Yes.
Like not by like Bluetooth or something.
Wi-Fi, via Wi-Fi, yes. You can connect to your friend's notebook via Wi-Fi.
Oh, is it like hotspot kind of stuff?
No. As ad hoc is like walkie-talkie. So you can enable, so on the Windows you may disable. So let's say how to enable. So if I'm sharing my screen, so you can have the ad hoc network in there in a mesh network, in a NetSH. You can do this by doing it, okay, in Windows. And there is it's a long time ago, 8.11 set was like 20 to 30 years ago, okay? Now we have hotspot. Now we have hotspot, meaning your device become an AP and the others are connected to, okay? That is a leader and the subordinate, leader and the slave, the master and the slave. But there is an even concept. Like if you go to the field, you want to talk to the others without any infrastructure, meaning you can set up as an ad hoc and you can still work on as ad hoc network, talk to your neighbors via Wi-Fi. There's many mechanisms to setting up this. So your computer can do this. If your computer cannot do this, meaning they are the violation. It has never happened. It's not happening. Okay.
So like if there's no Wi-Fi signals that we can use, but we need to communicate between two nodes, two computers, then we can use via ad hoc. Is that what?
Yes. Yes.
Okay. Gotcha. Thank you.
Thank you. So Wi-Fi standard. Oh, well, it's non-standard. In 1997, it started from here. It's about 23 years, right? So we started to use this. Max rate, typical throughput is important, and 0.9 Mbps, which is very slow, and work in 2.4 gigahertz. We're going to talk about this. 2.4, 5 gigahertz, 2.4, 2.4, and 5, and 5, and 2.4. So N was a groundbreaking performance, and like killed the market. So there is AVG, they're just playing with it, and this is their performance. Okay, then B is called Wi-Fi 1, A is called Wi-Fi 2, and G is called Wi-Fi 3. They are not sequential, okay? So on the market, you can buy this, AX. AX size of your notebook. There's multiple antennas, like at least 9 antennas around it. Okay, so if you look at the throughput, it's over 1G. It's really, really fast. AC, so 802.11 AC with the using Wi-Fi in the 5 gigahertz, and Wi-Fi 11N is most commonly used. So we don't use these commonly, but N and AC is usually being used by your device. So whenever you purchase the notebook, 802.11, AB, PAGN, and AC and AX. So your latest Samsung phone says an AX. Okay, so if you want to know detail, so you can click the link. So what we care is about the typical throughput. So end performance, how fast can you do? So as you look at this, who's the winner? OFDM. They are all OFDM based, orthogonal frequency division multiplexing. Then there is many standard. Okay, 802.11. Not just AX, but there are many more. They are candidate, and among them, they'll be our future. So in 802.11, there are not just ABGN, there's AC, AB, AF, AH, AJ, and all the way, then the BE is there. So everything has their own character. So if you look at in here, the bandwidth is a bandwidth, what we know is the frequency is not limited to 2.4 or 5. There's sometimes with the millimeter wave, which is 60 gigahertz, and there's much more. Li-Fi. Li-Fi means light-based communication, like in the sea, how they communicate. Blink, blink, blink. What does that mean? Okay, something like this. So there is also Li-Fi, and it will be established in the 802.11bb, and all this kind of things. So they all have their own characteristics. If you look at the 802.11ai, so AI is new mechanism and faster initial link setup. So every name is like their own characteristic. BE is extremely high throughput and something like this. Okay, go back to the slide. So how do you make your own standard? What's the successful scenario? How do you name after, how do you make your Wi-Fi name after you? Let's say 802.11 David Choi, DC. How can you make this? How can you be successful? So in a Samsung, in Korea, there's Samsung and Atri. I'm not sure about LG, but LG is a correlation with the Ericsson. So there's a Sony and all other vendors. What they do usually, so they are not just doing their own, they are not just doing the current business. They are always try the future businesses. Future businesses meaning, what's going to be next? What's going to be next? They always, this is going to be a standard. This is going to be next standard, next standard. And they are keep proposing next standard, next standard. And if you are the main author of it, then you can name the standard. Hey, not BB, no. Why BB? I want a DC. Why? Because I'm David Choi. Something like this. Okay. Then if it is selected, so Samsung is the main provider for 802.11 DC, and everyone else should follow their standard rules. Okay, meaning they lead the market. Everybody wants to do that. That's a $1 billion business. Okay. Also, so how to be successful in the business? Let's say you are selected as a standard, and how you be successful? So a long time ago, Korea was a very strong candidate in the next generation network. Then we called, now we called LTE. At that time, we called the 3GPP, and we called the WEEK6 as a part of the 3GPP. Something like this. WEEK6 was led by Korea, and LTE led by US. And WEEK6 was like 3 years earlier than the LTE. What happened to this? Who using WEEK6 these days? Nobody. Okay. Even use your algorithm, your standard selected by the standard. Then you have to have enough money and you have to have enough power to continue and keep pushing it. Okay. We are living in the legacy and the power under the US and what they want. And we have to follow. We have to lead the market, meaning we have to understand the flow of the business. Okay. So creating a wireless connection. So AP, we understand what is AP. So on the ceiling, which provide the wireless network, it periodically broadcasts SSID. Oh, SSID meaning, hey, I'm IGC guest. How frequently? So 10 times per second. Hey, about 10 times per second. Why is it necessary? So the AP's goal is provide the internet connection. Then meaning they have to sell their ID. So their goal is broadcast their ID, then everybody knows their existence, then people can be connected. Okay, so they are sending in 1 Mbps. Why? Because even the very poor performance Wi-Fi device to the fancy one, we have to fit into the poorest performance, that everyone has a same opportunity to be connected. If I broadcast my ID in a fastest speed, then the poor device cannot hear because they don't have ability, right? So we have to broadcast in the slowest manner. Then every Wi-Fi device can hear your existence. And the Wi-Fi standard leaves the connection criteria open to the client. Okay, here's I am, then, oh, I want to connect it to IGC guest. How can I do? There's a step-by-step, okay? So first thing I need to do, I need to know the existence of the AP. Then I can connect it. Then Wi-Fi spectrum is divided into the fixed number of channels. In Korea, we are using 11 channels. In China and most of Europe, 13 channels, and Japan is 14 channels. So we are a small country, right? Korea is a small country, but China is a big country. Japan, Europe, they're big countries. So we cannot do it by ourselves. We have to follow the flow. But if I am a China, if I am India, then maybe I can do myself because I have own market, which is big enough. So the main strategy of the Korea is, okay, let's follow the leader. Okay, that is how we survive. And I think it is good strategy. Just work with the leaders, work with the giant. So not all channels are isolated and they are overlapping frequencies. How they solve it? OFDM, right? Orthogonality. Then in North America, only channel 1611 are recommended to BNG. Why? So go back to the point. Some chat there. So David, I'll mark your question after this. Okay, 8 to 11. So look at this. Look at these pictures. So let's say there is 11 channels, 1 to 11. Let's say there's 13 channels. What if I'm using 1 and 2? They're overlapping. Even we are using OFDM, they are overlapping. The best way to do is distribute it completely. So therefore, 1, 6, 11 is the best choice, right? If you are not using OFDM, orthogonality, then we have to use 1, 6, 11. We cannot use 8, 8, and 9 because you are overlapping. Okay, that is why we talked about this. And 1, 6, 9, 1, 6, 11s are recommended. So David says, So reason make the latest the faster. Do they use a wider spectrum of frequencies? What is the reason that makes the latest are the faster? Do they use a wider spectrum of frequency? Oh, because the technology evolved. When the new technology evolved, then the long time ago, we didn't 10 years ago, we are using very slow internet. Now we're using the fast internet in a given environment. So the frequency is a given. We cannot extend it. Okay, thank you. So there is many ways to make your internet faster in the view of the vendor, in the view of industry. Evolve the technology and lobby the politician. Meaning, I can evolve in the via the technology. I can do 10% improvement, 20% improvement every year. With the politics, new spectrum, then you can your performance like 4 times better. Okay, so there is a policy approach too. Okay, sure. So we now understand why is the 1, 6, and 11. And 802.11a has 42 channels, not like 11, not like 13, which only 24 are used in North America, and only 12 of them are used to. So they actually have 42, but 24 of them are enabled, and only 12 are actually used because of overlapping frequencies. So we roughly have 11 to 13 frequencies. So if you look at the detail of the 802.11 standard, okay, we understand what is physical link. We understand what is a data link. So phase change, DSS infrared, DSS OFDM, DSS meaning frequency hopping spread spectrum, DSS direct sequence spectrum, spread spectrum, and orthogonal frequency division multiple. We understand what it is. So in the lowest level, how can you mix your signal? This is BPSK. If you have 4, QPSK if you have 16, QAM, and OFDM is using orthogonality, and frequency hopping is in a given frequency. I'm not just sticking it, I'm just keep hopping. Why is the frequency hopping is important? Do you know that? No. So frequency hopping is important because if I keep using same frequency, then the others are not able to share the frequency, which is a common medium. Also, if you keep using the one frequency, your communication is estimatable, meaning it's very prone to error and it's very easy to be attacked. Also, if you keep hopping it, very hard to estimate your pattern. Also, your frequency, your communication is more secure. And all distributed meanings, in the view of the fairness, everyone gets the fair opportunity. Okay. So in the MAC layer, there is a DCF, it's distributed coordinate function, or PCF. PCF is point coordinate. It is contention free. It is contention based. Okay. Then 802.11 is standard. Are you going to do the contention free? Are you going to do contention? Contention meaning there's AP, which give you even opportunity to, if you want to connect it to me, let's connect it to me. Oh, you know what? Like if I am the host, if you are a member of it, I'm giving you equal opportunity without competition. 1 and 2, then 3 and 4. It's sequentially. So David says the random, the hop random. Yes, random means the following the random table. So random table is shared but between sender and the receiver. Therefore, your receiver estimate the random frequency, random hopping sequence. Satisfied?
Yes, sir. So they share like a table that's between the receiver and client.
Yes. Okay. So, we are very familiar with the CSMA, carrier sense multiplexes. Why are we doing this? because we have to share and multiple by a multiple. And CA, collision avoidance. We cannot do collision detection, but it is easy to do a collision avoidance. Okay, let's see how does the Wi-Fi works. Oh, we understand what is DIFS and SIFS. Previously, before I start to talk, I sense for DIFS, it is fine. I can initiate the communication. If I am timing for replying, okay, I don't need to fully wait for DIFS, but I can wait for SIFS, which is much shorter. Then I can start to respond. Okay, so last lecture we discussed about it. Okay, I can assume you understand this. Okay, starting, send backup to 0, then persistent strategy, wait for DIFS, send RTS. Okay, can I send it? And set a timer. Set a timer meaning inside a timer, if I'm receiving a CTS, okay, did I receive it? Okay, I receive it. And send, wait for SIFS, and send actual frame you want to deliver, and set a timer. What's this timer do? Waiting for the act. If you receive the act, okay, communication succeeded. Okay, let's go back to there. A CTS is not received, meaning increment the backup. Okay, then backup, is it limit the backup limit? Backup limit is usually 7 times. If not, if it is exceed the backup limit, I'm giving up. If not, I'm doing this again and try to be successful. And if your egg is not delivered, then increment the backup and try to do again. Okay, now we understand the flow chart of the communication of the Wi-Fi. Okay, so CSMA, CA, nav, network allocation vector. So we understand, oh, in the source and destination, source wait for DIFS and send the RTS. Oh, now I'm replying, so don't need to wait for full DIFS. I'm only waiting for SIFS and send the CTS. Wait for SIFS, send the data, wait for SIFS, and send the act. All these others, whoever received RTS, go to nav, right? To avoid the hidden network, hidden node issue. So in the nav, they go to sleep. Okay, they don't even sense the carrier because they know, oh, there will be communication for that period of time. Okay, so when the station sends RTS, it includes a time how long it needs to be medium. Okay, and the receive the RTS, the communication will be reserved by them for how long. Other stations set their nav timer and they don't transmit and they don't even sense it. Okay, DIFS, we understand what it is. SIFS, we understand what it is. So example of the repetition of the interval. So beacon frame and contention free. So beacon frame, so I have different mechanism, AP and your members. Okay, so who wants to be connected to me? So I do the poll. Then everybody is, hi, I want to do. In this case, it is competition free. So who want to talk to me in the next period? Hey, hey, you are first, second, third, fifth, and sixth. Okay, then we do the poll and wait for SIFS. Okay, you are selected, then you are sending with the act. All the others, you are waiting for your time. Okay, then you are periodically doing this contention-free mechanism. Okay, so this is the contention-free, and there's new contention. So you can lock it, contention-free, and the contention. If there's contention-free, the mechanism is very simple. Who want to talk? Hey, I want to do. Okay, you are first, second, and third, and fifth, sixth. Okay, then they start to their own communication in the end. Okay, let's do it again. Who wants to talk? Okay. So detail of the frame format. So if you look at the frame, so frame control is FC, and D is the duration of the transmission that is set to the knob, and SC is a sequence control. Define the sequence number and frame to be used in the flow channel. So we have to remember this, and the basic set of this, you will keep using this. In the second homework, it is related to I think the third homework is related to the Wireshark. And your final project is also related to this Wireshark. Then you have to understand what's the packet look like. So what this number meaning? Okay, so subfield of the full control field, and that there's a version information, there's a designated, and if you set the more flag meaning it's more fragment, and retrial, if it is retrial, and more transmission, more retransmission means retransmission, and all this as the sender. So whenever you send the frame, the header have to include this one. It's very short, 1 bit, 1 bit, 1 bit. It may look long, but if you look at all bit, okay, if any of those are checked as a bit, I'm reading 128. Oh, that everything is one, everything is 0 except 1, right? So sequentially. Okay. So control frame, frame control, duration, and source address, and destination address, and your actual full control services, and full control, frame control, and duration, and your address. So RTS, hey, can I talk to you? Can I talk to you? Meaning this is my address, you are there, okay? CTS is, okay, you are clear to do, okay? Then frame type is 1, management, 2, control, 3 is a data, okay? Meaning 0, 1, 1, 0, 1, 1. So 3 different types of it. Then we don't usually use a 0 and 0 for the reservation purpose. 1 is management, used for initial communication between station and access point. Control is used for RTS and CTS and ACK. And data is used for carrying data and control information. This is actual communication. And if the header is 1 and 0, I don't need to read it, follow. I don't need to decode follow. And if it is 1, 1, and it is not for me, I don't need to decode it. Therefore, you can save your energy. And let's talk about the hidden node problem in AP mode and wireless network. Oh, now we understand B and C are hidden node from each other. Let's say B is talk to A, and C does not recognize B's communication. And if C transmit, it hinders communication B and A. Okay, so by doing a CSMA-CA handshake, the RTS, CTS, they can prevent the hidden node. How? Send the RTS, okay, here's the CTS. C received the CTS, therefore go to knob. And use of handshake, prevent the hidden station. Hidden node, we just talked about this, right? If B wants to talk, send the I. Can I send it? Sure. Then all the others who's potentially hinders A's reception is they go to knob. What about exposed node problem? Exposed node problem is not clearly solved. Say C is exposed to transmission in A and B. So C wants to send D, but here's A talking to B. Okay, in the communication, it is possible because when A is talking to B, B is receiving, and when C talks to D, A is only receiving. Therefore, it does not hinder the communication. They two is coexistible, right? By having an RTS CTS, is it really possible? Let's think about for 2 minutes, because I'm the only one who just talked for a while. And let's think about this. Is it really exposed station problem solvable like this with the RTS CTS? Okay, let's think about for 2 minutes. You know what to do. Okay, how to solve the exposed terminal problem with the RTS CTS. So exposed station is solvable with this. Let's talk about why is it not, if you think it is not possible. So I'm gonna pick 예은. After Yeun, I'm going to ask Seungjae and Hojin. Yep. What do you think? Can you solve the exposure problem with the RTS CTS? Seungjae?
Maybe we change the place of the stations.
No, place of the station is fixed.
Oh, is it? Right then, I'm not sure about.
Okay, so Hojin?
I'm not sure about it either.
Okay.
I think I need more explanation later.
Okay, so I'm picking the students not because I like you most, but the attendance and some of you are just keep replying to the question. Then I want to distribute evenly. So I usually pick someone who has a lower score in terms of the attendance, meaning attendance raise your voice in the class. Okay, so I'm picking you not because of I like you most, not because of I don't like you, but based on the attendance and the participation. All right, so this is use case of the handshake to solve the exposed terminal, but it actually does not able to solve. Let's see. A is talk to RTS CTS, and so my communication, I want this to happen. In theory, it's not an issue, okay? So there is communication in A to B. C is a hearing an RTS, but does not hear a CTS, meaning, oh, I can send it, right? Then I can send RTS. RTS is not an issue because B is a receiver and the D is a receiver. Oh, okay, you are clear to send. But C is not able to decode this CTS because A's communication and D's communication is overlapped. Therefore, exposed terminal problem is not solvable with the RTS CTS. Okay, so in this case, it does not work. So RTS CTS is resolution for the hidden node, but it didn't solve the RTS CTS, and it didn't solve the exposed node problem. Okay.
So can you explain that again? Because like since C wants to talk to D, why is A also talking to C? Like it's sending RTS and receiving data from us.
Okay. So we are talking about wireless network, meaning we are only directional antenna. If you're using directional antenna, okay, I can talk to you, but if I am talk to everybody, then there's someone who behind me also hearing my voice. That's the character of the wireless network. That's the character of the wireless character, right? So let's say A is talk to B, meaning A's communication is also over here by C because they are in the same communication range.
But wouldn't C also know that A is not talking to him, but rather it's talking to B, so it can ignore that packet?
Oh, good point. So I can ignore the packet, yes, but I have to, so this is an issue. Okay, let's repeat this. So I want to talk to, A want to talk to B, C want to talk to D. Okay, to solve this exposed node problem, it is possible case. It should allow, but it's not able to allow. Why? A is talk to B, then to do that, I'm using RTS CTS. So RTS CTS, hey, I want to talk to B. Okay, you're clear to send. Okay, here's my communication. No issue. But in the middle of the communication of A to B, C wants to talk to D. Okay, C, okay, I think I only heard RTS, but I didn't hear the CTS. Maybe I can communicate. Then I start to communicate. I start to send the RTS. D just receive an RTS clearly. Then send the CTS. No problem. But on the receiver of the C has to receive the clear CTS messages clearly. But C is not able to receive CTS message clearly because signal from A to B and this message is overlapped.
Like that part, Professor, that's what I'm not getting is that, like, since C did not send, A did not send clear to send to C, he should not, like, the data should be like ignored. Isn't that
Okay.
correct?
So we have to understand what is medium. Medium is what we are sharing. The air is the medium. Okay. When someone talk, okay, if I'm let's say David is just across me. I'm talking to David. While I'm talking to David, and someone else wants to start to communicate in the very vicinity. And if they start to talk again, then my voice is overlapped, and David cannot hear clearly because medium is contaminated. So I'm only able to decode properly when there is only one sender, one receiver. If there is two senders, they speak different contents, then if there is receiver, they cannot understand either of them. They cannot choose one.
Oh.
Okay. They are
so it's
listening
corrupted,
to,
that's what you're saying.
Yeah.
So you can't like decode like specific node, like signals coming from a node.
Okay, if I am talking to you and there's NAR just beside them, both of you try to talk to you in a very fast way in a data link, you cannot hear, you cannot decode properly, right?
Got it. Thank you.
All right, great. Thank you. Okay, David, great point. Thank you. So, physical layer of the Wi-Fi. We understand what is 802.11. Okay. A, B, G, N, A, C. They are using frequency hopping, distributed spectrum, OFDM, orthogonal distributed spectrum, and they are using 2.4, 2.4, 5 gigahertz, 2.4, 2.4. FSK is frequency shifting key, and phase shifting key. We know what the QAM and PSK and different mechanism, and rate is what we get. You know what? So we understand what the basic terms, right? Then what is ISM band? Why we keep using 2.4? Why you keep saying the 5 gigahertz? Why are we able to use this? Okay, in the frequency chart, most of the frequency is assigned by the incumbent. Incumbent meaning the someone who paid or someone is authorized to use it. So if I'm showing FCC frequency chart. Okay, this is frequency chart of the US, dominated by and authorized by the FCC. FCC is federal frequency certification. What is FCC acronym? FCC rules. What's the FCC stand for? Federal Communication. What's the C? Federal. Federal Communications Commission. Okay, that is FCC. So this is frequency chart. If you zoom in, it is all used by someone else, not all located, because people can hear this frequency. So after the people can hear, so from here it is designated for radio, designated for radar, some purposes. Oh, there are some purposes, meaning someone who has money or military purposes already allocated. And I want to use it. Which frequency can I use it? Okay, so FCC is common in Earth, common on Earth. So there, we call ISM band on Earth. If you're using ISM band, you can use this. Then that's the concept of the ISM band. So because all the frequency is already auctions and there is already incumbent, then if you're not, you are free to use without permission. That we call ISM band. ISM is in industrial, scientific, and medical purpose band. If your communication is one of these category, you can use it without permission. But your power level is limited by the government. We call 30 dBm, and which is 1 watt, 1 milliwatt. Those levels are, you cannot exceed those levels. And there is 900 megahertz for 26 megahertz bandwidth. And there's about 80 megahertz. And there's about 125 megahertz. It's allocated for ISM band. It usually says if your frequencies are lower, it is more expensive. Why? By the characteristic of the frequency, if the frequency is lower, your communication can reach further. Your frequency is higher, you can use the higher communication, the higher data rate, but the communication range is shorter. So we usually said if the frequency is lower, then it's more expensive. So we are using 2.4 gigahertz. This is 2.4 gigahertz, what we're talking about. Hey, 802.11 AC, 5 gigahertz, you are allowed to use. So we are opening, keep opening these frequencies. Something like communication for already assigned for the satellite or moon communication. The moon communication is very rare and they are not using that frequently. Then we can use for the human being, for the data network. That concept is called a white space, and we're going to talk about white space in later sections. Now we understand what is ISM band. And physical layer of the 802.11 FHSS is frequency hopping spread spectrum is if there is a digital signal in 1 to 2 mega, meaning digital signal, meaning my messages, your actual messages. We sometimes call the baseband signal. That baseband signal is modulated to 2 level or 4 level. We need to do this, right? Because we have to add redundancy. Also, we have to add the levels of communication. You remember the baud rate, right? Then random sequences and synthesizer and mix it together. Then transmit it by analog signal. As even we call the digital communication, there is a one level, 1 point. Communication need to be analog. Even we are using today's digital communication, we are using the analog at 1 point. Even when we say, oh, it is completely digital, we are using at 1 point, we are using an analog because we have to share the medium, the air. Air is analog and the air cannot be digital. Then if you're receiving this, remove this pseudo random code, then you can decode your actual messages. And DSS is simple. Your baseband signal, your actual information using chip Barker sequence. So 11 chip Barker sequence, meaning if you're using 1 mega, you are amplified 11 times. So 1 is representing 1, 1, 1, 1. Those are 11 on. So completely different sequences, but this means 0, this means 1, something like this. Then receiver can decode more precisely. more robustly. Then you make the barcode sequence, then you're 11 times more information than using a modulator. Then over the air wireless, the over the air and analog. Okay. Then infrared. Infrared, what we are using for remote controller. So your baseband, your actual messages, an encoder make it 4 to 16 and 2 to 4. So 2 times or 4 times more information, adding redundancy for better communication. Then you're using a pulse position modulation, then go to the analog. So 802.11b using CCK using 1 to 4 and 1 to 8. We know what they mean, 1 to 4 and 1 to 8. Why? We have to add that redundancy to make your communication more robust. Then this amplified information goes CCK selector, the pattern you have, then go to modulator, then analog. Then the receiver do the exact reverse way. Okay, what about Bluetooth? Bluetooth we are using every day, right? Bluetooth is for PAN, personal area network, right? Then Bluetooth is called PAN, or we sometimes call it Piconet, because it is smaller than wireless. It's because it is smaller than LAN. LAN, PAN, Wi-Fi is Piconet. Okay, in a Bluetooth, there's always leader, your notebook, or let's say your iPad. Your iPad is leader. Then your Apple Pencil, your earbud, and something else. Your wireless keyboard, your wireless mouse is subordinate. So primary is iPad, and they want to be connected to a primary. Okay, how they do? So what if there is a multiple primary, multiple cascaded? Okay, say this is keyboard with the mouse with one Bluetooth. So this is your iPad and connected by a keyboard. That keyboard is secondary connected to your mouse. This is common configuration, right? If you want to connect your wireless keyboard and mouse set to the notebook or iPad, you are only using one module, which is connected to your notebook. Then that keyboard become a secondary primary and secondary. Then when they are work as secondary, they are using as keyboard. When they are using primary, they are using when they're connected to mouse. Okay, so we call this scatternet. So cascadable scatternet is feasible in the Piconet. Piconet scatternet in the Bluetooth. Okay, so this scenario is a common case. Ultra wideband is also PAN. Ultra wideband is different. So we're going to talk about ultra wideband later. Okay, after the Bluetooth. So we understand what is a Piconet and we understand what is a scatternet. Okay, so Bluetooth layer. It is very similar to the Wi-Fi, but it is some characteristic. They have a radio layer and baseband layer. Baseband meaning your actual information. Radio is what you are using between digital and wireless, digital and analog. And there is control designated, audio designated. Because when the Bluetooth is designed, audio is the earphone was the main target. So they made the one pipeline. And if there is a data, you have to go to profile and L2 cap layer. L2 cap is logical link control and adaptation layer protocol. That in between data is coming to do, and there's control signal. Why do we need the control signal? Because Piconet and scatternet, we have to have slave and the master and cascadable. Okay, so Bluetooth layer is a radio layer, roughly equivalent to the physical layer. It uses 2.4 ISM band, and it divides to 79 channels. The bandwidth is very small and 1 megahertz, and use FHSS and 1,600 hops per second. hops per second and 1,600 times. And so each frequency lasts only 625 microseconds. Okay, this is dwell time. Dwell time is very small time. It dwell very small, and hop, hop, hop. Dwell time is very short. And baseband layer, roughly equivalent to the MAC layer, and use TDD, TDMA. TDD is a time division duplexing, time division multiplexes. And similar to walkie-talkie, using different carrier frequency. Okay, this is the Bluetooth layer. So this is key in the Bluetooth. And if I have only single secondary, meaning your iPad is connected to your Apple Pencil. So one to talk to, and the other, communication from iPad, then communication from Apple Pencil, and iPad and Apple Pencil. What if it is multiple? Then primary keeps having 50%. Okay. Secondary, only if there is two users, they are only using 25%, 25%, and primary 50% and 50%. What if there is a four? Four secondary, meaning they're only 10 each. Let's say if there is a five subordinate, they are only 10 each, and primary takes a 50, always. Okay, so leader takes a 50% at all time, and the secondary always get the proportional to the member of your subordinate. Okay, so this is the frame format of the Bluetooth. So there is access code. Your Bluetooth always requests the access code for the security. If not, everybody will just connect to your Bluetooth. They have to know your passcode. Okay, we call it access code. Okay, then so access code is 72-bit field that normally contains a sync bit and ID of the primary to distinguish frame of the one piconet from the another, and addresses up to 7 secondary and 0 mean broadcasting. So up to 7 is rough communication, the robust communication, but in theory, Bluetooth, it can connect up to 15, but it is not recommended. So define the types of the data coming from the upper layer, and F is flow control, S is a sequence number. Okay, so this is Bluetooth. So the David is asking what is the ultra-wideband? Ultra-wide, what's the characteristic of the ultra-wideband? So there is a Wi-Fi communication in some kind of 2.4 gigahertz, channel 1. Oh, there's LTE, much lower frequency, 700. Oh, there is a, let's say WiMAX, and 3.5 gigahertz. Oh, there's new frequency. Okay, whenever we draw it, I see this distinguishable and strong pattern. Ultra wideband doesn't work this way. Ultra wideband work in, I'm using wideband very low signal. Then my data rate is slower, but my communication is very well spread. But if you can, so I can distinguish from this guy to this guy. Then if I extract the communication, then, oh, I'm still there, I'm still alive. Ultra wideband can be used for many things. Ultra wideband is sometimes used for long range communication because I'm using ultra wideband. And ultra wideband is still in the research level. It is not commonly used in the industry yet.
Professor, I just found it on the internet. Apple's trying to use ultra wideband to detect the location of each devices. Is that
location?
What makes ultra wideband possible? Yeah.
Okay.
Ultra
wideband is very famous, very good at localization. It has characteristic. When you are doing localization, ultra wideband has the best characteristic for the localization. I don't know what the Apple is doing, but UWB is known as the best application for the localization. So this picture's showing the characteristic of the communication. 4G Wi-Fi has a strong pattern signal. So ultra wideband doesn't send the strong signal, but very low signal is distributed very widely. So even there is some communication, they are not hinders the others, but their communication is still there. If you have a proper receiver, you can receive it in a wideband.
Then the data that's sent within UWB will be very slow as well, right?
Yes, it's not. So to make strong and faster communication, your communication needs to be sharp and high level, high energy. Energy is well distributed, and very low level, your communication is reliable, but the strong level is very short, very small. Therefore, it's very hard to achieve the high data rate. Okay. All right. Anything else? This is what I prepared today. So I will upload the slide right after the rebuttal. And I have one computer. I'm using my desktop. I can only upload from desktop. I don't know why Google blocks it or no, but it is only able to upload from that computer. So I'll upload it today. All the slide and all the videos I have. All right. Thank you guys. Any comment? All right. Thank you. All right. So for the rebuttal, you can remain for the rebuttal. Go ahead. Question? Janar?
Oh, I said like goodbye.
Okay. Thank you.